Hey all. So I have a confession to make. I have about 20 videos like this I would love to record, but I always paralyze myself thinking I'd like to clean up my office a little more, I'd like to get the script a little bit tighter, I'd like to get some better graphics. But the way COVID-19 has kind of interrupted our lives and I need to get some material out there for my students, I need to put a halt on that kind of stuff paralyzing me. And I need to get some curriculum out there for my AP students. I normally work with Mr. Snyder at Loudoun Valley High School, and this is some material for my AP students at that class. Talking with Mr. Snyder, we had to end the school year a bit abruptly, at least go to remote learning, when there were still a couple of topics that we wanted to cover for the AP exam. And the AP exam is going to go on this year, so Mr. Snyder's planning to cover that material, and I thought I'd give some supplemental curriculum that's the kind of stuff I would normally walk through in class a little bit. And while I'm tailoring this to Mr. Snyder's class, really this would make sense for any student in Loudoun County that needs to prep for the AP exam, and probably any student across the country that needs to prep for the AP exam. This curriculum would be enduring. You can use it in years past now, but right now in particular, that we have to cover these topics, distance learning for the AP exam, it makes sense to get this out there as quickly as I can right now. So the two topics are searching and sorting. And so I've worked up some curriculum here. And to show you where to get it, this is a GitHub page. Now you don't need to worry about learning GitHub or anything like that. I'll put a link to this page in the description below. And you can see there's this clone or download button here. So the whole package here is a searching directory, a sorting directory, and a README that tells about what this curriculum. This is self-guided learning here. This is something I expect you to be able to do on your own, although Mr. Snyder and I will be around for questions. If you're not in those classes, I'm sure your teacher would love to assist. But if you click on this clone or download button, you can see there is a download zip file. And you download the zip file, you unzip it on your machine, and you will get a directory structure that looks like this. There's the README file, which is something you can read on your own, a searching directory with binary and linear search examples, and a sorting directory with two examples, one using Java's built-in sort and one with an algorithm we define here, and then a bunch of notes. I'm about to go over that right now for you. So here I'm looking at JGrasp, and this is the editor we use at Loudoun Valley. A number of high schools in Loudoun use JGrasp. Some use Eclipse. If you're an Eclipse user, I'm sure you can figure out what to do. Just a different project structure. No big deal. So there's the README file. It steps through and everything the order I want you to do stuff in. But first is the searching directory. And the first in there is going to be linear, with our linear search example. We pull up that code, and there are some comments in the top that tell you exactly what this is about, set up a little bit of curriculum, and then some comments that step you through the code. We'll worry about this search code after I set up how we use it. Here we have our main where we enter, and we have 100 random numbers between 0 and 999. We're going to look for element 352, and we're going to do that by passing the array of data and the element to our search method. And if it finds an element, it's going to say data element found at index. Otherwise, the search will return a -1, and we'll just say data element not found. So let me show you this running. I run this code, and it tells us data element 352 found at index 98. If I try to search for something I know is not in there, like 1001, it comes back and says data element 1001 not found. So let's look at how this does this. Now, here we go. We give it a fancy name like linear search, but you can figure this out, right? We just have a for loop that is going through from 0 to the end of the array and testing that element. If it's the element, yay, we found it, and we return the index. Otherwise, if we get all the way through the data without finding it, we return -1. Well, that seems pretty simple and obvious, but it leads to some questions. And I ask them down here at the bottom, like, with 100 data elements, how many compares are we going to have to do? If it's the first element, if it's the last element, or just thinking in percentage, if we have to do that to find, if we do that 100 times, on average, how many compares are we going to do to find the element we're looking for? Do the answers change if we're looking for 10,000 or one element out of 10,000? And is there a more efficient way we can do this? And of course, yes, there is. And that is what a binary search is about. So I have two implementations in here, binary searcher and recursive binary searcher. But let's start with the search driver. Again, same idea. Comments up here at the top that can set you up for some self-guided learning. We start with the same data that we had before, but this time it's sorted. And we'll talk about sorting in a minute. That's not the point of this. But let's say somehow our data can magically get sorted, and we want to look for a given data element in our data. Well, I'm going to call binary searcher search data and element. And just like before, if it returns -1, it's not found. Otherwise, it's going to find the data element. So let's look for data element 895 and run. And it tells us it's found at position 94. So let's look for 1991. That's not in there. And it tells us data element not found. Following the same pattern, I have some questions for you down here at the bottom. But let's go look at binary searcher and see how it works. Again, same pattern, comments at the beginning. But now this works the same way you would if you say we're opening a book and looking for a specific page number. What do? You open the book to someplace about in the middle. If the page number you're looking for is less than that, you look in the first half of the book, turning to about in the middle. And in 3 or 4 searches, you can generally narrow down on the page number you're looking for. That's exactly what a binary search is. It looks at the left and the rightmost element as the 0th element in the array and the last element in the array. And then in this while loop, it figures out a middle element. And hey, if we happen to have the middle element, we found it and we return it. Otherwise, we split it in the middle. If the middle element we found is less than what we're looking for, we change the left-hand value. Otherwise, we change the right-hand value. And we just keep looking over and over, narrowing down left and right. And if it ever gets to the point where left is greater than right, the while loop will stop, and then the whole thing bails out and returns -1, which is exactly what our code here does. And we saw it could find our data elements. Now, over in Search Driver, we can also change our implementation by uncommenting this line. And so we comment out that line, we uncomment that one. And now we're using our recursive binary searcher. And sure enough, I run this one, and it tells me 1991 not found, but I look for something like 804, and it finds it at index 85. So how does recursive binary searcher work? It is exactly the same algorithm. It's got some comments in it to tell you what's going on, but it's structured slightly differently. We have our first search that takes the integer array of data and the candidate. It figures out the left and the right, but then it defers. It calls to this internal search, passing in our left and our right that we've calculated. Now, for recursion, we have our base case. For our base case of not found, right is less than left, and we return -1. We didn't find it. Otherwise, we calculate a middle, and if that middle equals our candidate, we return the middle because we found it. If we didn't find it in one of those two cases, we now need to recurse. If the middle is less than our candidate, we search the bottom half, calling internal search recursively. If it's greater than, we call internal search on the upper half. It will recurse down, either finding the element, eventually hitting one of our two base cases of finding it or bailing out. So the same algorithm, just recursively. So we studied recursion earlier in the year. That should at least seem familiar to you. Maybe a bit magical, but worth exploring until you're comfortable with it. So how do we get that data sorted? And for over here, I have two examples, sorting 1 and sorting 2. Now, sorting 3 is left as an exercise for you, and I'll talk about that in a second. If we look at sorting 1, we're going to let Java do the heavy lifting here. Now, there's an old joke in software engineering, but what's the difference between software engineering and computer science? And that's in software engineering, sort is a method you'll call. In computer science, it's a class you'll take. And I'm about to make that joke real for you right now. So let's look at our first example of sorting. We create an array list, and I populated it with 1,000 elements, randomly generated. I'm then going to print the first 20 random numbers for you, just to show you that it looks pretty random. And then I'm going to call collections.sort on our data. That sends that data into the magic of Java, and it comes back sorted. And then we're going to iterate through the first 20 elements and show you that it's sorted. And then I ask some comments and some questions for you to think about based on what you just saw, but let's run it. First 20 random numbers, and they look pretty random to me. And then first 20 sorted numbers, and now they look pretty sorted. So hey, that worked. Somehow Java did the heavy lifting. Well, now let's tunnel down on that. So again, more comments, more questions, designed to be read as a self-paced lab. And I'm pointing to some other YouTube videos. Now, these are not mine. These are some awesome videos that show various algorithms animated so that you can understand them as a robot comparing colored balls. The video that I point to here shows two, bubble sort and quick sort. So I'm going to show you how bubble sort works in a second. But first, to show you I have no tricks up my sleeve. Again, more comments to insertion sort, merge sort, heap sort, some other visualizations. But my code should look largely the same. We're going to generate 1,000 random numbers. We're going to print out the first 20 random ones. We're going to call our bubble sort. And then we're going to print out the first 20 sorted numbers. Run it. And here we go. Our first 20 random numbers, and then sorted. Okay, so let's talk about how bubble sort works. Now, the thing about bubble sort is it's the algorithm we teach because it's easy to understand, but it's one you'd never really use in professional practice because it's pretty bad performance-wise, and you'll see why. What this does is it has two loops, an outer loop and an inner loop. The inner loop is going to compare each element. You know, these two are the same, these two. Now, this one's greater than, so it moves it. Oh, this one's greater than, it moves it. And it moves it all the way up. And the first pass through of the outer loop, the biggest element will end up in the last position. The second time through outer loop, the second biggest element will end up in the second to last position. The third time through, the third biggest element into the third of the last position, and so on and so forth. But if you think about that, every element is being compared to every element over and over and over. And it can be pretty inefficient. So easy to understand, horrible performance. When you watch the video, it'll show you that quicksort is a much better algorithm, as are the insertion sort, merge sort, and others that we'll take a look at. But that's the catch for bubble sort. And the idea is you can ask yourself the questions in each of these labs. Some of them, like I'm done with asking you questions, but I want to challenge you with watching one of those videos, maybe even looking up the algorithm, creating a sorting3.java, and implementing the algorithm for yourself. Now, there are other things to learn about sorting. For instance, it's rather boring sorting integers. I mean, we know their order would be, but it gets more interesting when you start searching things. Like, imagine I want to take every student at Loudoun Valley. There are a number of different ways I can sort them. I could sort them by their last names. I could sort them by their grade and then their last names. I could sort them by their GPA. All kinds of different ways we could sort them. And we'll talk about that in another video. There are some advanced ways to be able to pass in the desired way you want to sort things, or the value that you want to sort things by. That's with a technique called adding a comparator in Java. And we'll talk about it in the future. In the meantime, hope everybody is having a fun distance learning end of year. And sorry I'm not seeing you all in class, but I'll have some contact information below if you have any questions for me about the content in these videos, or anything else for that matter. Hope to see you soon. Bye.